Okay, so it's 11:05. Let's start. Did you had any lecture before? I think you had 1 hour, huh? You started at 10. So here we are at day 4, back to Darmstadt. So today we will talk about concrete durability, and we have a 3-hour session, 3 times 60 minutes. First 2 sessions are more theory, and then last session it's also a lecture, but I will try to make it more to show you the fusion model also in Python, and maybe also 10 games how you can also model acid and CO2 attack and, to predict phase assemblage. So we are here in the 3 days. So first day we talked about the cement hydration, then the puzzolans and kinetics of cement and puzzolanic hydration kinetics, how you can model it, and now we talk about the concrete durability. And this is actually all related. So this is the first session. We will have 3 sessions, and the first one is actually on chloride attack. This is the most common durability issue. And here you can see this in Germany. It's mostly de-icing salts. But in general, yes, the chlorides, they are like 66% of the damage caused in bridges to the German highway network is due to chlorides. We can see also here in Germany, bad construction 18%, and then there are other durability issues: carbonation 5%, fatigue, freeze-store resistance 5%, and alkali silica reaction 3%. But the majority is due to chlorides. So it's not only de-icing salts, it's also the marine environment. This is Croatia, my home country, in the Adriatic Sea. So this is a very famous bridge that connects the island of Krk with Croatia. This was from my master thesis a long time ago, 20 years ago I think. I already stopped counting. And we did a lot of maintenance for for the maintenance of bridges. This is also a famous torpedo launching ramp in Rijeka. They were building torpedoes, for the World War II. So this is actually one of the first. They were launching torpedoes and testing them. And yeah, this is very old building, and you can see a lot of corrosion here. Reinforced steel concrete, reinforced concrete, steel reinforced concrete, and we got a lot of data on these kind of maintenance works and repair works of bridges, concrete structures, reinforced steel structures, not only marine but also continental. So the combination of carbonation and chlorides. And my master was actually to do machine learning on all these, to do the neural network on all these data that was collected during the maintenance works. So this is also one example. This is why the picture looks so old, because it was a long time ago. It was one of the first neural networks applications on the durability of concrete. I made 2 publications on that, and most of the publications were on compressive strength and neural networks, but this one was on concrete durability. So you can see here the concrete cover and very strong, harsh corrosion. And yeah, from past back to now, or even the future. This is the EU project Nature CPV. You can see the link here. There is a nice video. And actually, in this project, we are building the prototype for photovoltaics. That's why PV, photovoltaics. So to have floating farms of the photovoltaics in the offshore, so in the sea environment. And then, of course, the harsh ocean environments or sea environments. We need to build it to make it durable. Also the big waves, we have to design it to endure big waves. And it's made of UHPC, so ultra high performance concrete with floating, and on top of it, it's the photovoltaics. I will show some examples later. So back to the theory. So this is a diffusion reaction problem, because the chlorides are diffusing through the cover depth, through the pore system of the concrete, and then of course the cracks, they accelerate the penetration, but the more you have the corrosion of steel, the bigger the volume expansion and the more cracks, and then at the end you have the spalling effect. This is typical spalling, but this is actually, then at least you can see where the damage is. The most critical is when you don't see the damage, but inside the steel bar is corroding. And there is an example, I think in Italy a few years ago, there was a bridge collapsing. Okay, that was the pre-stressed problem, and there one of the pre-stressed corroded with a pitting corrosion, and then the whole bridge collapsed. Also in Germany, I think, in Dresden, so Eastern Germany, okay, now we don't have this division anymore, East and Western, but in Dresden there was a bridge a few years ago, 1 or 2 years ago, that collapsed. But that was mostly, they say it's mostly because it was not so good error in the building during the design phase, during the building of the construction of the bridge. So this is a very important issue also, and we have the penetration of chlorides through the concrete cover. This is the initiation phase. We have the chloride penetration depth, how deep it comes. This is just initiation, and then it goes penetration, because it reaches when it reaches the steel. This is also actually damage. So when it reaches the steel bar, then it goes very, very fast. And also the accumulation of chlorides at the steel bar level, we have the propagation. Because I will show you the mechanism, chlorides act as accelerators for they depassivate the steel. I will show the chemistry behind. So when we reach the maximum acceptable penetration depth, or the amounts, we have very strong, this is then the end of the service life of the structure. So a little bit about the radix reaction. This is actually linking to the first day with the chemistry, why we have this complexation reaction, if you remember. So basically, why is steel passivated? Because we have the high pH, and that makes the iron hydroxide layer on top of the steel, which is, protects the steel from corrosion. So this is the passivation of the steel at high pH. So that's why we also need high pH, because we want to create this passivating hydroxides, iron hydroxide. At low pH, we have the solubility. We increase the solubility of iron hydroxide. If you remember, same what we did, same principle, chemical principle, what we did the first day. But also now we have the complexation reaction of chlorides. Also, if you remember the first day. So we are building this ferrochloride species, complexation species, hexachloride ferrite ions, and they pull this equilibrium to the right, because there is a equilibrium constant which is pulling actually no, okay, it's one constant. Sorry, I wanted to say that we are pulling this equilibrium to the right. So because this iron makes iron ions, also the D and 3 valent, and these ions are then actually one equation is missing here. Let me write it to fully explain it. So we have because this is already a summed equation, which also includes the complexation. But if you would not have the chlorides, then we have the iron hydroxide as a solid, and this one dissolves in water, of course. It dissolves to iron 3 plus 3 times OH minus. And because we have this now, the iron is pulled out by this reaction, because this iron is taken to form iron complex. We have the equilibrium constant here for the complexation, so this has to be, it's taking some iron away. In equilibrium you have less iron here, and because you have less iron here, that means you have to dissolve more iron hydroxide, increase the OH actually. So you are making the iron hydroxide more soluble. So either by lowering the pH or increasing the chloride content, that means lowering the iron here content, you are increasing the solubility of iron hydroxide. So this is the same principle I'm trying to teach you, and you can see it's very important. This is what explains why the chlorides accelerate, depassivate the corrosion of steel, basically because they are making the iron hydroxide more soluble. So, but of course, in corrosion we also have the cathodic reduction reaction. So the diffusion of oxygen is also important, because this is then governing the rate of the total corrosion rate. So the overall redox reduction and oxidation reaction, we need chloride and also oxygen. So chlorides are important for diffusion because they explain the depassivation, the initiation phase, but when you enter the propagation phase, actually also both the chloride diffusion and oxygen is important, what determines the rate of the corrosion reaction. So here the picture of the reinforcement. So the rebar reinforcement bars, steel bars, and here we can see we have the surface concentration, and then how the chlorides diffuse inside the concrete, and here we are reaching some critical threshold. This is the critical threshold when the steel starts to become depassivated, and now you know that this actually also depends on the pH. So this critical threshold is a function of pH, and you know why. Of pH and of chlorides. So it's not only, I mean, in standards we have the critical threshold for chlorides, but this is actually also pH dependent, and you know why now. So this is typically 0.4%, and per mass of cement. This is the concrete cover depth, so the thicker the concrete cover depth, the better for durability. So this is the most important design parameter, and you should make as thick as possible this cover depth. And if you put here, this is the RCM test, when you spray it after diffusion, when you spray it with silver nitrate spray, you can see the silver chloride, which is in this silver color. So you can exactly see the penetration depth, how the chlorides come in, and you can see here some ITZ effect and aggregates effect. And this becomes very important in, for example, in if you have low water cementrations and also slag, because then the microstructure is very dense, and then the ITZ, the porous zones, starts to, you know, to be the path, the critical path that the chlorides follow. So how to engineering model, how to predict this diffusion? It's FID model code 2020. There is also an update bulletin. I was also involved here, but more for the acid attacks. You can find this bulletin here. And yeah, it's a very nice guideline. It's published, I think, last year. This is from the original model code. So basically it's just a diffusion of modified second fixed law. We have here the apparent diffusion coefficient. Why is it apparent? Because we have the effect of it includes all the, you know, all the parameters, because it's very simplified model by diffusion. We don't have only diffusion, we have many, we also have a reaction, and then also, you know, convection, or many things happening. But if you simplify it only as a diffusion, then this parameter is apparent. The most important part is the reaction, the binding of chlorides, and this is why this is apparent. We have the error function here, and this apparent diffusion coefficient is also time dependent, because the concrete is hardening. You have the putzons which are slowly reacting, so they are improving the microstructure. So this is also time dependent, not only because of binding, it's also because of binding, but it's mostly because of, or at least it's believed it's because of the continuous hardening of the concrete, but I also would argue it's also because other effects, like binding effects and pH effects on binding. So it basically, we consider here the total chlorides, meaning the free and the bound chloride. So the total is free plus bound. We have, if this is a pore, we have the chlorides that are bound to the solid, and we have the free in the bulk pore solution. So this would be then the bound, and this is those are the free chlorides. And if you do the mass balance, yeah, the total is the kilogram chlorides per cubic meter of concrete, and if we have the free chlorides, also kilogram chloride per meter cubic of pore solution. We can derive, this is the second Fick law. It's basically, this means that the flux that comes in is equal to the flux that goes out. That's why we have this this is the flux, and this is the change of the flux in this direction. So what comes in must go out, because there is no reaction. If you would have a reaction, you just have to add reaction. But if it's in steady state, yeah, this is the steady state. What comes in must go out. So if there is no accumulation, this is zero. Then you have this Laplace equation, which is basically the second derivative of the concentration. I will explain this later. I'm just explaining the diffusion equation, how you derive it. So basically you have the concentration gradient. If you take the second derivative, which basically means the change of flux. So how much flux, how many chlorides, the rate of penetration of chlorides, what comes in the steady state should be equal to what goes out. So this is exactly Laplace. The change of the flux is 0. Or if you have accumulation, so if something goes in is higher than it goes out, you have the accumulation in the pore solution, and this is exactly the change of the concentration in time. So accumulation is equal to the input flux minus output flux plus the generation. We don't have the reactions here yet, but actually they are here in the diffusion coefficient, which are actually in the accumulation. You can also model it as in accumulation. That's why the reaction rate can come into the diffusion, because actually then it becomes part of the accumulation. So it's like accumulating in the, but now not in the pore solution, in the total concrete, because we are having the total chloride concentration. But then only if the effective diffusion coefficient, which is basically the first Fick's law diffusion coefficient. First Fick's law gives you the flux. The flux is proportional to the diffusion coefficient and the concentration gradient. And if this effective diffusion coefficient, or the Fick's law for diffusion coefficient, is constant, and if the binding isotherm is linear, so that the change of the concentration is a function of the free concentration. You know, the binding isotherm, this would be the binding isotherm. So if you have the free concentration and you have the total here, or bound, it doesn't matter. Then if this is linear, then the rate, the DC, this slope is constant. So this is the binding isotherm. And if this DC, the big C divided by d small c, small is the free, big C is the total, is constant. This is the slope. Then actually this part here is constant. Because we can write, you know, this is the, we also, I need to make one more step here. So the first Fick's law is dc is the big C divided by delta T is the change in flux. So the dt, and then we have here this cancel out. We have this d small c divided by dx. We have the effective diffusion coefficient. But how to get the big C now? Because we want to know, you know, this is because we have the diffusion through the pore solution. So if we multiply this by the Tc divided by small, basically it's this part, then we are getting, but then also multiplied by dc. Then you get this part. You came up with a big DC. You know, if these two cancel out, this goes up. You can see it like this. So this is how you end up with the definition of the apparent diffusion coefficient. Is the effective diffusion coefficient divided by the slope of the binding isotherm. The rate of change of total chlorides is a function of free chlorides. And then you have here the final. So this is, maybe you are familiar with 1 plus, you know, the porosity, and this, that depends on how you write the units. But this, in this way, if you write the units, then the apparent diffusion coefficient looks exactly like this. It's the effective diffusion coefficient divided by this binding slope. So now you can see it's the physical meaning for the diffusion, and also like for the, you know, effective porosity, tortuosity, and the microstructure, just physical geometry. And this part is the reaction part. And this part actually can go here, then it's part of the accumulation, what I explained before. But of course, yeah, the world is not linear, makes it more complicated, but we are still using the solution which is based on linear, so it's engineering approach, but you should be, of course, then aware that the reality is much more complicated. And that's why, yeah, simple models are nice, they are good, they are simple, easy to use, but they are also you should be aware of the limitations. So the most important being that the binding is not linear. So the binding is non-linear. First we have the, you know, typically it goes something like this, and it's also a function of, that's why it's called isotherm, it's a function of temperature, pH, very important also, but also temperature very important, so it's changing. And also a function of course, composition of the how much CSH you have, how much aluminates you have, because the aluminates, they have usually this instantaneous binding, and then you have the physical binding on CSH. So changing the composition of CSH, of maybe cache phases, aluminates, which bind more, I think, more chlorides, and having more aluminate in the mix binds more chlorides. If you have more aluminate, calcium aluminate, you have this formation of Friedel salt that binds chlorides, and this is then, yeah, more binding is better, because then you have, but it's also more non-linear. That's why the L03 system, when you put the clay system, I mean in general, any mixture with clay which has aluminates and it's reactive, it improves the durability, not only because of the pozzolanic reaction, which creates more CSH, which again binds the chlorides and lowers the pore structure, I mean it refines the pore structure, so it's changing the effective diffusion coefficient and also making more binding. But you also have the more calcium aluminates like Friedel salt that also more strongly at the beginning they bind the chlorides. So time dependent diffusion coefficient in Eurocrit code or the FIB code, model code 2020. It's modeled by that you have, you know, the migration coefficient basically from the RCM, rapid chloride migration. And this is also one, because this rapid chloride migration is not really the real diffusion coefficient. It correlates, but it's not the real diffusion coefficient. But this is the approach, because you need rapid measurements and also rapid predictions. We cannot wait. But of course, you can take the chloride profile after in surface light, but then that you can do only when you do maintenance. But if you design new concrete, for bridges, you have to predict, and then you need rapid measurements. So if you make the measurements after 28 days, but nowadays they are changing this to 56 or even longer, because of the more and more pozzolans inside, which are actually slowly reacting, so we need better reference with longer hydration time. And then here is just the, the aging factor, typically 0.3, and how that makes it changing, how the apparent diffusion coefficient changes with time. So this makes the diffusion coefficient also time dependent, of course. And you can see this influence of time. Typical value 1 to the power of 10 of minus to the 10 of power of minus 12 meter second per second, meter square per second. And then with time we have for different n coefficients, and this n coefficient depends on the binding. This is why I'm telling you it's also binding. It's not actually it's also, of course, it's also how fast the pore structure refines, so it's also the hydration, okay. But this n depends on your mix design, how much putzons, how fast they react, and they have some binding, I would also say, effects. So this is, if you have very slow putzon, fly ash that's not reactive, it takes a lot of time to react, then this exponent increases. Yeah, that's how it's explained, because the pore structure gets more dense because of the late putzolanic reactions. So there are some aging factors with the influence of the type of the cement. So CEM1 would have 0.26, so very fast, there is no big change between 28 days and the final. But if you use, fly ash, you have very big aging factor coefficient, 0.7. So now this is the fixed second law. You can implement this in Python, Excel, wherever you want. And we want to predict when is the depth, the cover depth at the still level, when is it reaching the critical chloride content. And then when it reaches the critical chloride content, then we need to, do maintenance. We should remove the old contaminated cover depth with chlorides and do new repair mortar. So here's some example. We will solve this example later. So let's say that the surface content, the surface concentration, that's the boundary condition, it's 3%. This can also change with time actually. But let's, this simple model, there are models that you can also change this with time. In this simple model, let's fix it, 3% of the cement mass. We have this diffusion coefficient and the cover depth is 3 centimeters. And we have the n coefficient of 0.3, so we can plug in these values and then you can see how this apparent coefficient is actually reducing. After 20 years, we will go from 10 on power minus 12 to actually 0.13 10 on power minus 12. That means almost an order of magnitude lower in diffusion coefficient, which is very, very, very important for prediction. So after 20 years, we have an order of magnitude reduction in the diffusion coefficient. So this is the critical parameter you need to, that basically determines also the service life. So if we plug in the values, we will get that the chloride, critical chloride content at the depth of the steel bar is 0.16% after 20 years. And the threshold critical, no, not the critical, sorry, this is not the critical, this is the predicted chloride content is 0.16% and the critical amount is 0.4% per mass of cement. So it's less than 0.4, then we are good. So this structure will last at least for 20 years. So now we can predict if at the 30 millimeter with the time. So this was the 20 was 0.13, we were here, but now we can plot at what time do we reach this critical chloride concentration of 0.4 mass percent of cement, and this is what we had at 20 years, but now we see that this structure will last for 40 years. And then after 40 years, but maybe even before, we should do some maintenance. We should replace the concrete cover. But it's a statistical problem. Yeah, it's not, this is deterministic model, but the problem is statistical because we have the variation of the concrete cover depth. We have also uncertainties in parameters, and that's actually in the model code. You also already have it stochastic approach, that probabilistic approach, that you can have uncertainty. So what is the uncertainty that at which year you should make the maintenance, with how much percentage of uncertainty or certainty. So you can also have different cover depths. This is for design. Of course, if you increase the cover depth, you drastically increase the service life of concrete. Or you should actually make the concrete better, that is more, binds more chlorides and it's more thicker or less porous, more better concrete. Always more cement, but that makes it also less sustainable, of course. So it's an interplay, optimization problem. But of course, the more durable it is, that's again sustainability basically. Here in Germany, I was driving on the highway last days, and actually, there are a lot of highways here, very dense. It's one of the most, busiest places in Germany, Frankfurt area. Also the Cologne area is called Ruhrgebiet. It's very dense with highways, many trucks. Always, I'm amazed how many, you see a line of trucks just going all day long. So much traffic here. But there are also many lanes, 3, 4, 5 lanes in this area from Darmstadt to Frankfurt airport. You have 4 lanes almost continuously. And then, there are also many crossings of different highways. And then I see this, because I'm almost 10 years already, 11 almost years here in Germany. And I see some bridges being repaired, and actually what I saw, mostly they completely, replace old bridge. They start building the new bridge parallel to the old one for the new highway, crossing the highway below. So what I saw basically is they just build a new bridge. So it even doesn't pay. It seems like it's cheaper to make a new bridge with very good concrete quality and very good new bridge than to repair the old one. So they just build a new bridge and then they descend the old one. This is what I saw in several places. But of course, maybe it depends on which bridge. So here you can now play with the model. There was the RILEM TC, this is the old technical committee chloride ingress modeling. It was to benchmark chloride ingress. Professor Quenders was chairing this. I was helping here. I also drafted, I wrote the chapter 3 on marine submerged together with the French guy, Anthony Sauvet. And we basically benchmarked a lot of models. Here are the models, different models. We use the FIB as a reference. Those are all the big guys in this field using models, and then we were predicting. I also had here one model for the This was the reaction diffusion model where I explicitly modeled the chloride ingress by the isotherm, nonlinear isotherm, Freundlich and Gmuir. So there were analytical models and numerical models. And there were some quite advanced reactive transport models. SD-TRIM, for example, and more advanced analytical models. And there is one case study, very well defined case study from Norway, I think, or Sweden, I'm not sure. I think it was Norway. They did a very well documented case study, and we used that case study to benchmark the models. So you will see some examples later in the Python. I think this part I will explain later. Yeah, this is a reaction diffusion model. If you want explicitly to model the reaction, you should take it away from the apparent diffusion coefficient. Then you have your real effective diffusion coefficient, and you have your reaction term. And this is, again, you have the change of the bound chloride. So this is the amount of the binding rate. We have the 1 minus porosity and the density, because it depends just how you define the, here is the mole per meter cubic of solution. And then this is the binding isotherm. And then with this model you can predict the total chlorides and also the free chlorides. The free chlorides are here. Those are the bound chlorides, somewhere there is a very high amount of binding, and you have the free chlorides. And I implemented this in MATLAB to solve this partial differential equation with reaction and diffusion. This was an example of one model. There were many more advanced models with the reactive transport models, even using, you know, the moisture, convection, quite advanced models were also inside. So I did here some examples, because this case study actually had a 2-year exposure, 5 years exposure, 10 years and 20 years exposure. It was a very nice study. So we could actually, what we did, we gave the modelers 2 and 5 years, I think. And they were supposed to predict 10 and 20 years, and we didn't show them these results. And then we could benchmark how well they predicted. And then we did even one more round. We told them, okay, now these are the results, because this is what you also have in, you know, in a structure. You need to predict, but then you can also, after 20 years, you can also see. When you do the maintenance, you can take the profile, go to the site, measure the chlorides in the concrete, and then you have the profile after 20 years, and then you can also correct your model. So we did the same exercise. So these are the measurements points, and those are the predicted by model. And actually the dispersion of the model prediction was huge. There were some over-predicting, some under-predicting. It was a huge difference between a huge dispersion of the predictions. I didn't show it here, you can see it in this book. I think here I even have the research gate, so if you want I can share with you. So that was the old TC. Now we have the new TC meeting. This is the chair by Pranoy, probably you know Pranoy, in Miami University, Indian guy. I don't know where is he exactly from, which part of India. Pranoy Suraneni. And he's chairing this with William Wilson. Yeah, Pranoy Suraneni, William Wilson. And we just published the paper in the Materials and Structure. It's open access, so you can see it. It basically reviews all the methods which you can use to predict the diffusion coefficient. And it's also focused on blended cements, so that's why it's very timely, relevant. and it's focused on paste. So how to downscale, how to do, you know, fast measurements on paste, mortars, and then so that you don't do it on concrete, but also concrete, and you can compare, and if you can maybe, you know, speed up the measurements, so do the downscaling, because then you can also test the blended, the putzolans, how they affect the diffusion coefficient. So we reviewed we focused on blended cement pastes. Of course, we have to compare with mortars and concrete. And also different methods. So this is, you know, if you have concrete, this is how it would look in the mortar. But this is the mortar, sorry. But this is the blended cement concrete. This is what I was telling you. This is ordinary Portland cement, and if you have, you know, the slag, here you can see how really these ITZs around the aggregates, how they basically determine the critical path, because that's the porous region. And here now we also have mortar. It's also UHPC, basically. If you have very small aggregate, then you have basically a lot of, this would be like a UHPC, and you have binder paste without aggregates. So this is that's how the RCM, rapid chloride migration, looks like in our lab. And we are now making a round robin test in this technical committee, that we have 4 different mixtures: the ordinary Portland cement, fly ash, with blended the slag, and with the LC3, with you know, the limestone and the clay, 30% clay, 33% clay, the LC3 mixture. And on those mortars and pastes, after 28 days, no, we had 1 year exposure, sorry, 1 year exposure, 1 year hydration. You have these samples, and then the exposure for 28 days to natrium chloride solution, 0.5 molar. It's coated in epoxide, so that we have one-dimensional diffusion. Then you can do the, you know, the grinding for the Volhard titration method, or you can what we did the cross section, and then you can use the microscope, like with the micro XRF or EDS. We have EDS here in our lab, so we are developing a methodology how you can use EDS microscopy to get the chloride profiles. So this is the round robin test we are currently running. You can join in if you want. So we are comparing different methods, and we have different blended mixtures, how we can measure the paste and also mortar. So that's currently ongoing in this technical committee. It's a working group in 4, and I'm chairing this group. So further mix design, if you go more to concrete, you can see how also these ITZs, they affect, they are the more porous regions which affect the penetration. And yeah, there are also coatings. You can use coatings, of course, like styrene, butadiene, and rubber coatings, typically used in US at least 10 years ago. I know that they were used. Nowadays, I'm not sure if they are environmental, maybe for environmental reasons they should be replaced. There are other coatings. I reviewed these coatings in this paper. Sealants, siloxanes, SBRs, actually that's experimental work done in lab. And then how, you know, what are pros and cons of each of them, environmental impact of also. So you should use water-based siloxanes. And then how they lower the water absorption, gas permeability, they lower the chloride penetration, and also abrasion wear. Yeah, this is the multiscale. If you go into the cement paste, you have the diffusion of chlorides in the cement paste. Also ITZ is very important. And here I come back to this UHPC, which we are making for the floating farms. And there we are using slag blended cements in UHPC, ultra high performance concrete, with steel fibers. And this, we were, a few weeks ago, we were in Spain. This is the factory which is producing these UHPCs. We are making the first, design of this kind of structure. And you can see here the floaters. Those are UHPC 1 cubic meter. Here it says 3.2 tons of concrete of UHPC. They are hollow inside, so they are floating. This is the Esteban. He is the CIO of this company, and they are now in this UU project. And interesting here, they did this is a beam. It's a pre-stressed. So if you lift this beam, you can see the cracks. You can hear the cracks because it works in the tension pre-stressed. And of course you have the cracks if you lift it, and you can see the cracks. First you can hear them, and then we also saw them, because when you wet it, you can see where it's drying. So there the water goes into the cracks, capillary, and then you can easily see the cracks. You can measure how many cracks you have. And this is after, when you put it down, actually then the water goes out. So it's very, very interesting. So after, this was right, and then when they put the beam down, you can see how the water, capillary water which went in, how then it goes out. So you can see in this 20 centimeter how many cracks you have. So this is all important, because then the chlorides go in, so we have to design this structure for very big waves. Of course, and then the chloride ingress is important. Yeah, here also, if you have this model, and here if you have a cracking, you also you can include this cracking in the model. So that's the first part. Now it's 12. So I'm exactly two minutes before, but we started 5 minutes, but it doesn't matter. Maybe we can do the break now. Then we can have more time for, we have time for questions, sorry. If you have some questions. So how would you measure diffusion coefficient? What kind of equipment do you have in lab? Or if you don't have, what would you plan to buy to measure the diffusion coefficient? RCM is the typical method. But you know what? It doesn't work for it doesn't work for when you have steel reinforcement. It doesn't work. So how to measure it? Because you need a voltage. You accelerate by voltage, but when you have the steel fibers inside, it disturbs the method. There are some paper actually showing it, but we tried it and it doesn't work. Fundamentally, it cannot be used for measuring rapid core migration coefficient of steel reinforced concrete. So how would you measure then? So what we are doing actually, they did it also, exposed it to the seawater, and also to, in the lab test, exposure of samples to, so like here, this method. And actually then, because of course after a few months, because it's UHPC, we only have, less than 1 millimeter penetration. But then we will use this microscopy. I have the samples here and we will try to measure, at least we can get, the profile at the first, in the first micrometer. Yeah, there is no other way. At least we have something. Yeah, or to go to the old farms that are already, 10, 20 years floating, and then take the sample and then see. But then again, the penetration is very low because it's UHPC. So again, this methodology, what we are developing, is actually quite useful. Any questions? Comments? So no durability in your lab. Or we are doing more 3D printing. I have some 3D printing examples later, I think. There is another project we are printing actually. Yes, okay, I see the question coming. I don't hear you. Still no sound. Sorry, now? Now? Now I should be able to hear you. It was... Okay, now, if you try now. I still don't hear you. Let me check the different... Maybe you can... Somebody can type the question. Then during the pause we can solve the issue.
You can just
Now
hello.
it's good. Now I hear you. Yes.
Yeah.
Hi.
Thanks. Sir, now the research interests are into the geopolymer concrete production. Can all these formulas can be applied to determine the chloride attack for the GAC?
Yeah, that's a good question. I think there was a RILEM TC committee with John Provis and Gregor Groth from BAM here from Germany in Berlin. There is a publication, I think it's also open access in Materials and Structures. They did the diffusivity of alkali activated materials. And yeah, what I know, it's that the binding is much less in geopolymers. So you cannot especially if you use geopolymers. I mean the true geopolymers that they don't have almost no calcium. Then the pores are very small, but they are connected and there is not much binding. If you use alkali activated materials like slag, then you have calcium, then probably you have also binding. I think this was the main result, but you need to check, yes. Probably you work with alkali activated materials, not geopolymers. Huh? So if you have calcium, then you have binding also, yes. Then this can be used, but I think they should be modified somehow. You can check. I would recommend you to check the so from Gregor Glut from BAM. I think if you just type technical committee and alkali activated materials and diffusivity, you will see that paper.
So how about RCPT analysis, sir? Rapid chloride permeability test. That's related to durability.
What is the? I didn't understand the question. RCM for the
RCPT, rapid chloride penetration test.
Yes, yeah, that's the bit. That's when you only measure the currents, huh?
Yeah.
That one is actually not so reliable. It's not so. I would always advise you to measure the real, to spray with silver nitrate and to really measure the penetration depth. Because the current gives you only rough estimation. It's better to really have the penetration depth. RCM, I would recommend you better to do the full RCM test, rapid chloride migration test, the anti-build, norm. I think I have it here. Yeah, this is the worst method you can do, the rapid penetration. I know it's the fastest, but it's also the most uncertain. Yeah, I removed the non-steady. I didn't put but this is the anti-build. I didn't put the norms. I forgot the number. Yeah, at least RCM. I would recommend you to do RCM test. You can also check in this paper we reviewed. We also discuss. Where was it? This. We also had some discussion on the methods. But for geopolymers, actually, because they are interesting for acid resistance, so I will talk about. You will see some geopolymers here for the acid attack. Okay, if there are no more questions, so we can meet in 15 minutes. That will be 12:25, huh? 12:25, we can meet. MITI, DTA, it's on carbonation and chloride penetration testing of alkali activated concrete. I shared the link with you in the chat. So very nice. You can see here the effects of how to measure it on alkali activated materials. And here I also, they are all open access papers. This is the one, maybe I can also share this link. And here you can see the methods. So this is the anti-build. It's also free available. That's the Norway standard. It's also EU standard. So this is what I would suggest you to do the RCM test, rapid chloride migration. And actually here you can see what we wrote. We didn't even include the RCPT test because there are some other tests, also interesting tests with penetration, but where was this text in migration? Yeah, migration tests, and then, yeah, this, I think you are referring to this one. It's the French, or the Canadian use this test also, I know a lot. The column test, so you are basically measuring just the charge passed, measure charge passed as an index of chloride resistance, but cannot directly determine the diffusion coefficient due to involvement of all ions. However, using almost the same setup, a steady-state diffusion coefficient can be theoretically calculated, as outlined in NT. Basically, I think it's measuring. I think it's not so difficult to use the same, almost a similar setup and to switch to empty build. I would recommend you to use the empty build method. Of course, there are differences, but I think it's the setup is. I think it will be easy for you to just follow anti-build on the same setup. So let's continue with acid. And now we go also to geopolymers. So if you are interested in geopolymers, we do a lot of research. 11 years already research on geopolymers with companies, and we try to bring this to the market, but also fundamental research, a lot of fundamental research on geopolymers. Especially I'm focused on acid resistance. Why acid? Because you have many these harsh sewer environments. For example, you know, we live in more and more bigger cities, and the sewer systems are, yeah, very harsh environments, and they actually, the concrete is after, you know, 5-10 years, you need to change the sewer, and then you need to dig all the infrastructure, all the roads to replace the sewers. So it's quite a big problem. But there is also wastewater treatment plants, food industry, a lot of, especially organic acids, agricultural industry, biogas in nowadays because of the energy crisis. CO2 sequestration also, but I think that's the paper I show you with they want the pumping of CO2 in the abandoned oil wells, but I think this is nowadays not so. It was interesting maybe 10 years ago. So we have different exposure classes. XA1, I don't know if you also follow this. This is like, but I think this is European, similar is in US. Probably you have the same similar things in India, exposure classes, so that the concrete should be designed according to the exposure class. So basically, when you define the concentration of the aggressive species or the pH in the table, then you define the class, and then you know the minimum, you know, water cement ratio and the strength and all these durability parameters. But what I told you in sewers, basically, yeah, you need surface protection. This is what I wanted to say here. Basically, in XA2, XA3, and there is a new class, XA4, all the classes require surface protection. So only XA1, only if you have very low chemical attack, you don't have to use. But in the EU, I think in US the same, you always have to use surface protections. And that means basically coatings, organic coatings, but the question is, are these organic coatings really good? Are they sustainable? There are also, you know, delamination, blistering effects. Are they environmental? And this is why we have a lot of research here on geopolymers, because we want to replace these organic plastics with inorganic geopolymers, which is a more, should be a sustainable alternative to organic. Because here you have to use it, so let's use the, you know, inorganic geopolymers. So we did a lot of study on geopolymers. This is a key paper, a milestone paper we did with Graz. Basically, I designed the geopolymers. They put it in the sewer. It was 2020, and was for 1 year in the sewer systems. And we demonstrated the performance of the geopolymers in sewer systems. And you can see this here. So this we had actually the UHPC was the worst material we could use. There were some Portland cement mortars, and you can see here after 18 months the degradation depth is very high. We compare it also with calcium aluminate cements because those are actually the real, you know, the real materials, the durable for sewers. And here are the geopolymers, which actually outperformed all those materials. We only had the leaching of potassium, but this was not detrimental for the strength or the coating performance. So you know, I will not go into theory of this sulfuric biogenic, but basically you have the, you know, the bacteria which eat the organic stuff, they thrive on it, and then they produce sulfuric gas, which then builds on top and then makes sulfuric acid, which of course is aggressive. You have the sulfate attack and you have acid attack, and this is a very aggressive environment where you need high performance materials. And but the coatings are also not so sustainable, let's say. The company where we were doing this demo with geopolymer pipes, actually they, in this factory, they had the linings, like polyethylene linings in the sewers, but they had also many problems with these linings. So this is how the UHPC would look like the worst after 1 year or a year and a half in situ in sewer systems. And you can see geopolymer maybe change color, but actually was really performing really good. We also did some research on using copper as a, you know, like but actually turned out that it's not so good idea. As a, you know, the copper is antibacterial property, has antibacterial properties, but we actually abandoned this idea. Although nowadays we see again many papers doing this again, but because you also have the leaching of copper, and then maybe it's the question, is it really sustainable? We also tried with zinc oxide, but I think only geopolymers, if you design them well, because you need to know how to design a good geopolymer, probably with alkali activated materials. We did just pure geopolymers without calcium, but if you add some slag in it, that would also improve I think the durability. Because, you know, the more calcium you have, the more soluble you make it, but it's also less porosity. So this is now I think I have this slide somewhere, but okay, I will go to it later. Yeah, you can see here also in the field conditions. We also did in the activated sludge tank. This is the water waste treatment where we have the bionitric acid, and the geopolymers were really always performing the best, even when you compare with calcium aluminate cements, which are, you know, 3 times more expensive than Portland cements. 4. Yeah, it depends also on the mixture. Geopolymer, yeah, it's more expensive, but it's more durable. So again, the FIP code, very simple engineering model. Here you can see also the exposure classes I was telling you about. So basically, it's not only the concentrations, it's also what kind of type of soil you have. Because if you have, stagnant clay soil, which is stagnant, then the boundary condition is not changing, so you don't have to, so the conditions are less harsh. But if your boundary condition is moving, if you have a moving acid, this is of course dissolving much more than when you have the stagnant conditions. So the sandy flowing conditions are much more than strict. The concentrations are much lower. And then you define the exposure class, and then you have defined what is the lowest water cementation, all these things. And basically all these classes require surface protections, meaning plastics or geopolymers, but they are still not, in the design codes. So how to then predict? So there is a very simple model. It's based on the square root model, because if you have here beta is 0.5, you basically have a square root, which is the fundamental moving boundary diffusion equation solution. But you have also the concentration here as an empirical parameter on the on the alpha. And alpha actually depends on the type of acid, because you have different types of acid. So if you have a soluble salt acid like a nitric, then you have this beta is 0.5. But if you have a protective salt acid like sulfuric acid, because it makes, protective layer, but it also closes the porosity because of the precipitation of gypsum, but it also makes cracks. So then you can change this beta factor. And you can have a strongest dissociation acid, which is basically means that you have a very high equilibrium constant. Then you can easily calculate the pH. But if you have a buffering acid like acetic acid, then this is the way how you can calculate the concentration of the pH from the concentration, or the concentration from pH, because this is a weak. Weak means that it's weakly dissociated. It's not weak in, that it's not, that it's actually even more, it has a buffer effect. Weak means that it's a weak constant. That means that you have weakly dissociated, that the pH is lower, but you have a high amount of buffer that can then provide more protons, more H+. So it's not weak. It can even destroy more concrete than the strong one for the same pH, because you have this buffering effect. Weak means only that it's a weakly dissociated acid, and this is strongly dissociated acid like sulfuric acid, and this would be example of acetic acid, so the vinegar. So the Ks is the dissociation constant, that's the equilibrium constant basically, which you know now very well from the chemistry. And the C total is the total amount of acid. So it's not because if it's partially dissociated, then the total amount is what is important. CO2 can also be regarded as an acid, especially if you have, not carbonation problem like from natural carbonation, but if you have really attack of aggressive, then it's called aggressive CO2. Like if you're pumping CO2 into oil wells, then you have very high concentration, supercritical CO2. This is one example of aggressive CO2, but also in soil, you have aggressive carbonic acid that then again, like here, you have flowing or stagnant, and then you have different exposure classes. So when you are building fundaments for buildings, high-rise buildings, like in Frankfurt, they make these high-rising buildings. Looks like New York, very high buildings. and then they need to dig very deep and make fundaments. And then the soil is actually very important, because then they have to make, the exposure classes. So we did some tests for them. Then they should, especially if they use, because all these exposure classes, they are made for Portland cements, or if you want to add slag or deviate from the standard, then you need to prove that the acid resistance. And that's what we were doing here for them. So this was example of the carbonation, what I showed you also, I think was on Tuesday, where this is the surface of the sample, and you can see calcium carbonate building on the surface and filling all these pores. So this is aggressive carbonation, and here if you have a crack, it's another paper from a PhD student here. She used the phase field model, so sealing of the crack. It's also self-healing in this case, and then you can see with time how the crack heals. So you can see this penetration of the front, how it actually seals. This is this front, how it's moving, and you can see how it's sealing the crack. So the acid attack, here you can use the microscopy also for the chemical analysis, and you can see if the acid comes from this side, you can see the depletion of calcium, decalcification, because of the dissolution of minerals. This is those are the aggregates, sand aggregates. This was the mortar exposed to acetic acid, and then after I think it was a few weeks, you can see that the 4.5 millimeters of the zone is completely decalcified. Yeah, it's one of those samples here, but for aluminate cement, actually acetic acid strongly dissolves aluminate cement, which should be acid resistant, but because of these complexation reactions, it dissolves a lot of calcium. And now you know the mechanism. Again, the equilibrium constants are important, because you can see here OH minus. So this is the calcium aluminate product, the stable one. It has a solubility product, and which should be constant. And if you are taking this OH minus away because of the acid, you are removing the OH minus. That's why you increase the solubility. And this is why that's the mechanism of the acid attack. Again, explained by the solubility constants. So you are increasing the dissolution of hydration products. Also, by acetic acid, actually, you are complexating the calcium. You are making calcium acetic complex, which is again taking calcium from the equilibrium ion activity product. So you need to even dissolve more. So this is why the calcium aluminate, although it's a very, very acid resistant material, it's not so, does not resist so much the acetic acid. So we are also working on reactive transport models to really understand, thermodynamic dissolution, what we saw here, the chemistry behind, also solubility of geopolymers. This is what I am developing. This is not yet available in the literature, especially not the acid resistant thermodynamic description of geopolymer. And then to link this in a reactive transport model for acid attack, we have fundamental research products on this. And you can see on cementitious materials thermodynamic modeling, when you are adding acid, you can do actually this with SEM GAMS already now. I will show you examples. So you can predict this, how the portlandite here, how it dissolves for acetic acid, and here is for sulfuric acid. When you are adding more and more acid, how the portlandite dissolves, then the CSH is dissolving, and you are precipitating silica gel, and the pH goes down. The difference with, so the acetic acid doesn't precipitate any protective salts, but with acetic acid we have the gypsum precipitation, but this is again a high volume of gypsum, a high amount of gypsum, so there is some critical volume that then makes cracks because it's expanding, wants to crystallize, and then expansive, and then you get cracks. So it is protective, yes, but it also makes your layer cracking, which then again allows new acid to come in. So we did a lot of tests on thermodynamics, a lot of mixtures with different acid concentrations with Portland cement and silica fume. Also for sulfuric acid, this is acetic acid. Sulfuric acid, there was this protective layer, so we could not really get the equilibriums because that's what the challenge with acetic acid. And you can see the model. So just by pure thermodynamic modeling, just by chemistry, fundamental predictions, without any fitting parameters, we were able to reproduce the experimental results. So this was very nice success. So you don't have to do, the actually thermodynamic modeling predicts very well the equilibrium concentrations of acetic acid. Of the sulfuric acid was not successful because of this. We could not reach equilibrium because we had this protective layer, and then this is why here we could not predict. So this was, kinetic control. We wanted to use equilibrium, but there was no equilibrium because there is a lot of cement which was not reacted by acid, was not detected. So this is why we could not predict here. But for acetic acid, actually, it worked very well. Also, the dissolved ion. But for sulfuric acid, actually, there was a very simple correlation with the amount of acid and the dissolved sulfate, and also precipitated sulfate. So the more sulfate you add, the more calcium sulfate you precipitate, and also dissolved. This is the dissolved one, and this is the precipitated one. So here is like a linear correlation, but then later becomes to be non-linear. So these are the volume fractions. You can see with sulfuric acid how the phase assemblage changes. This you can also now model easy in GEMS app online. I will show you this. Basically, you are dissolving Portlandite, CSH phases, but you are precipitating gypsum here. A lot of this, more and more gypsum. And with silica fume, you basically have just less Portlandite at the beginning. This is the Portlandite is lila here. So we don't have so much Portlandite. So that's the difference. This is the volume fractions with acetic acid, with Portlandite and Portland cement and silica fume. Again, less Portlandite. And you can see which phases are forming. You have thaumasite, strathlingite. Later it's dissolving. We have alumina gel here precipitating, and amorphous silica gel, also iron gel. Yeah, some conclusions. You can read this. There were some interesting conclusions. And now I will go to geopolymers. So you have aluminosilicates. Here you don't have calcium, basically, and this is what makes it acid resistant. So you have this, aluminate tetraeders and silicate tetraeders, which you have with aluminosilicates, like, for example, clay minerals, they are dissolving. You have potassium activators, hydroxide activators, and silicates, which then polymerize. So those are the tetraeders, aluminates and silicates. Silicate is neutral. This is the silicate tetraeder, and aluminate has one negative charge. And basically you are just linking those tetraeders. It's called polycondensation, because you are basically releasing water. Those are the oxo bridges in between. you are releasing water, so it's opposite to cement hydration, that you bind water. Here actually you are releasing water, polycondensation reaction, and you are making this three-dimensional very polymer. That's why it's called geopolymer, but it's made from silicate, not from carbon organic, but inorganic, from aluminosilicate polymer network. If you would polymerize this further and crystallize, you would get zeolites. So they are basically amorphous analogs of zeolites. And you can see this reaction written also chemically. You can see these oxo bridges here. And this is a big, yeah, this goes a big three-dimensional network. And what I told you here, we have the aluminate, which is negatively charged. And this negative charge of aluminate is compensated by alkalis. So these alkalis are bound to these aluminates by ionic bonding. And this is important because with acid attack we have leaching of these alkalis, and this is that's why I'm explaining this, because it's also important for the pH for the reinforcement. If you want to use it, then actually this pH very fast it goes down. It's by leaching or by acid. So these are the raw materials and characterizations that we use. Basically it's a mixed clay and very pure clay. This doesn't work so good, the pure clay. This is the Metamax commercial, but this clay is very successful. It has also high iron content, and it has elite inside. You can see the amorphous content. It's basically around 50%, 45% of metakaolinite. It has some elite, and the rest is quartz. With this clay we had very good properties. So we compare this with Portland cement, calcium aluminate cements. I will not go in all the details. Yeah, of course we are using potassium silicates, not sodium, because potassium is better, although it's a bit more expensive, but it's better because it's better rheology, but also less leaching. Yeah, here you can see the viscosity, and the molar ratio of silicate to potassium is 1.5, but now we are using 1.7, because with 1.7 you can transport this. You don't have, special, it's not hazardous, so you can, it's less alkaline, so you can transport it. You don't need special permission to transport this kind of silicates when you have the molar ratio of 1.7. That means less alkaline, more silicates. It also works very good. It's more sustainable. Here I wanted to show you can do the pH titration experiments. Yeah, basically you are dosing acid, and then you can see the neutralization capacity of the binder. And this is very important because you can see it here. For Portland cement, it has a very high buffering. So you are adding HCl and you are reducing the pH. It's in the powder. So this is just, you can say, almost equilibrium powders. You can measure the neutralization capacity of the binder. So this is because of the dissolution of portlandite and CSH here, and then you have here alumina gel, probably in dissolution, and then there is no buffering at low pH. Now for alumina cement, it actually has lower buffering capacity than Portland cement, but it has a better buffering at lower pH. And this is why alumina cement performs good in sewer systems, because here you have this alumina gel formation, which maybe also works as antibacterial because of aluminates, and you have closing of the pores at pH of 4. But if you go below 4, then you are dissolving this alumina gel, and then again you have a very high dissolution. Geopolymers, this is the novelty here. The first time I showed also how the geopolymers, and actually they don't have any very low neutralization capacity at the beginning, which is basically alkali leaching. The alkalis I showed you before, which are bound to aluminate, which compensate the aluminate charge. So they don't really buffer the pH very little. And then we have here the silica dissolution. Aluminate, mostly aluminate and silicate aluminate dissolution. And here is the pure. When you use pure clay, you have more geopolymer, so you have higher buffering effect. And when you use less pure with more quartz, like a filler, of course, you have less geopolymer and you have less buffering, but you have better, more dense structure. This is why this material still performs better than this one. And the same thing for the acetic acid, but this one shows you the complete picture as a function of pH. Yeah, this is a differential derivative of the previous one. And here I'm just comparing the different amount of, what is the difference in the binders. Portland cement has a low amount of aluminates. You can increase this if you add metakaolin in L03 mixtures. It has high calcium and silica, but those are have very high solubility. In low and medium, silica gel is the one that stays in low pH, in the acidic range. You have alumina gel, but very little. So if you actually increase alumina, this should increase also the acid resistance. And this is why alumina cement works better, because you have a lot of alumina, high calcium, but also high alumina. It's here below. And but you have low silica. And because of this alumina gel, which is very stable at pH 4, so that explains the good acid resistance of calcium aluminate cements. And now with geopolymers, you will have very high silica and alumina, very low calcium. Those are pure geopolymers. And then that's why we have alumina silica gels, which have very low solubility in medium pH. So this is how we explain the good acid resistance of geopolymers. And in between, you would have here alkali activated materials. If you are adding calcium, you are basically making the alkali activated materials less porous, but also more soluble, don't forget. So there is an optimum amount of calcium which would make it the best acid resistant. Yeah, here I also compare it with, different acids that you have here. Formation with Portland cement, you would have crystallization of ettringite at the beginning and later gypsum crystals. Alumina cement also gypsum crystals inside. This is what we also saw in this publication in CCR when we compare those degradations after sewer, in situ sewer exposure. But here you would have also gypsum, but some also alum salts. Those are the potassium alumino sulfates. Potassium, I think they are called alums in geochemistry. And it's acetic acid, you don't have any soluble salt precipitating, but you have the complexation, which makes all the minerals even more soluble. So this is the mechanism for geopolymer acid attack, which we have published in also many papers. And basically you can see that this proton is attacking first, it's an ion exchange of proton with potassium or natrium. So we have here the protons, so then those are more leachable. And then later this proton also attacks the aluminate, so we have the dealumination reactions. Yeah, I will not read these conclusions. I will just continue with how to measure the acid attack now. I also proposed a method how you can do the diffusion test. Also, if you epoxy coat your sample of the paste, you can then see how with different, liquid solid ratios, you can measure the ion leaching. So there are no standards for this. There is a water leaching test for concrete, also standard for acid attack of concrete, but for geopolymers they should be adapted, and this is my proposal here in these papers. We also did this was for acetic acid. There was a titration because for sulfuric acid, because it's a strong dissociating acid, so you need to dose it. Acetic acid you don't need to dose because it's always, buffering. And here are some results. And you can see how the cumulative fraction of leached potassium with time, and you could fit it to the simple diffusion equation. And with different, the stronger the acid, the stronger the acid, the leaching of potassium. So this is the amount of leached potassium in the solution with time. And here you have it for water, for very low concentration of acid, for higher concentration of acetic acid, and for very high concentration of acetic acid. And this one was on the red clay geopolymer. We did also, and you could see that this is almost 5 times increased the apparent diffusion coefficient. What I told you, we can model it with a simple diffusion equation. And with the white clay, those diffusion coefficients were actually two times or even 58 times lower. So actually these performed better. And this again we can explain by the here we have a bigger amount of geopolymers than here. But the problem with this is that this mixture cracks. It has very high dry shrinkage sensitivity, and this one doesn't crack. So here you can see the cracks and acid attack, and with this chemical analysis, we can do the mapping, EDS mapping, and then analyze the concentration of potassium aluminate silicate in depth. This is after 56 days in 0.1 molar acetic acid. This is just a paste. You can see quartz particles, but they are part of the clay. Quartz is inside, and but this is still paste. And you can see here how the potassium is leached out, and here on the surface we have dealumination of the geopolymer. So again, some conclusions, and here now I'm doing the modeling using a supercomputer how to do these acid models. And here I would like to finish with link everything together. So this is you need the microstructure, which was the first day. You need Putzolanic reactions to make it, to adapt the models for the current modern binders, which is, the clay or even geopolymers. You need to understand the microstructure formation, and then it's important also for the durability. And again, you have this multi-scale approach that you should go from microstructure, from the chemistry, from raw materials to the structure, and to be able to predict the performance of at the structural level. So with this, we ended the theoretical part. And now I can show you later, after the lunch break, how you can model the diffusion in Python, and I will also show you in SEM games how you can also easily with the process modeling, how you can model the phase assemblage of the chemical attack, CO2 or acid. We can see how the phases are dissolving, and you can model this also in the SEM games app. So simply by in this, process, you can again simulate all these minerals, also aluminate cement, LC3 system, and then you can add here leaching or ingress. You can define the salts and just simulate, and you can get nice prediction, thermodynamic prediction of the leaching and also the chemical attacks. So we have two things for the demonstration of the Python, how you can model the diffusion, and also how you can model the chemical attack in a thermodynamic modeling. So now I'm open for questions.
Professor, we had conducted acid attack test on the concrete.
Yes, what was the question? So acid attack on concrete?
The question is, for carrying out the SEM analysis of that tested sample, what is the process behind that need to be followed? Because we don't want to harm the equipment of the SEM.
You mean with this microscopy?
Yeah, this microscopy. What is the process
Yes.
with the samples? How it can be processed?
Yes, sure. That's a very nice question. So first, you can see all the details, I think, in this RILEM technical letter. This was an invited paper. And basically, you need to, because this was cement-based, so you have to do the cross-section because you are interested in the depth. So this is the cross-section. And then you have to polish it. No, first you should impregnate in epoxy because you want to preserve exactly the microstructure. So we impregnate it with epoxy. There is like under vacuum. You should. It's a typical preparation method for SEM when you want to preserve the microstructure. So you should dry the sample, but not too much to typically, 40 degrees, maximum 50 degrees drying, and then put it under vacuum machine, and then add epoxy, because that then sucks in the epoxy, low viscosity epoxy into the pores, and then harden the epoxy, and then polish the sample. And after polishing, there is like, you need to fine polish it with 1 micrometer, even less. You go stages with polishing. Is described here also inside. And then you can put it under the microscope. We have the environmental microscope, so we don't have to do the coating. We can use it under low vacuum. Some vacuum is inside, so we don't have to coat it with, conductive coating, carbon or gold. We don't need this because we don't want it, also because we want to analyze the elements. And then then basically I did, I think it's 100 magnification and then mapping of chemical elements. And there are 1, 2, 3, 4 sections of this. And then you analyze, you take area and then he gives you the chemical analysis of this area. So we have to do it manually per depth, and then you can get, for each window, we get the chemical composition of EDS for the smaller areas. It's similar what we are doing for chloride ingress. This is the round robin test. But now here you can see it on the acid attack, yes. I think in chlorides you have it nicer figure. Yeah, this one. Okay, here is 500 magnification, but I think we reduce this even to 100 magnification because then technician needs less time in, because they need to do, then they only have to do 3 times windows to go inside, 3 measurements, and each takes like 20 minutes for 22 minutes. And then later, when we analyze this data, we are doing the smaller areas where we collect the chemical composition. So it takes the statistical average chemical composition of each of these windows. And this is then per depth. At the beginning, we take more points because it's more interesting, and later is, there is constant value, so we can take bigger areas. Yeah, it's quite tedious to do it because we wanted to automatize it, like image analysis tools, but then the problem is that actually the EDAX software is fitting this EDAX to measure the composition. He can only do it in the software. So we cannot really, so we have to, it's difficult to automatize it. We can get the composition of each pixel, but then the pixel, he's fitting the composition to the EDX profile. But that 1 pixel is not enough because it's very low resolution. You need some statistical average, a lot of pixels to get a good EDS signal that you can fit it to get a good concentration composition. Maybe if you would use EPA, this is what we did here, but this was really, high resolution. This is very advanced technique. They did it in Graz. Oh no, it was later. It's a field gun, so you need really a good field emission. Where was it? Yeah, this one. This is field emission, very strong electron, very strong intensity, field emission SEM with electron probe microanalysis. Here, for each pixel, you can get very good signal. But in EDS, in normal SEM, there is not enough energy, or you need very long measurement time, which is not possible because the image drifts. So either you need very, very advanced technique, very high energy gun, field emission gun, and then you can, per pixel, you can really get chemical composition per pixel. But this is a rare technique. Not many labs have this. What we have in a lab is just normal EDS, which is also, we are very happy with it. But you cannot do really chemical composition per pixel because the signal is very low, and that's why we need to, sorry for this, we need to really take this many pixels to get a good signal that we can fit. But then we have to do it in the software, so actually we have to do it manually, unfortunately, to get this kind of nice profiles. So we are, yeah, we have to do it inside the EDX software. Any other questions?
Sir, one more question here.
Yep.
So when we talk about the activating the supplementary cementitious materials, either we can do it with a geopolymer technique or else we can go for the alkali activation technique. In geopolymer, usually the molarity would be the main concept to activate or to keep the dosage, but in alkali activation, the concentration of any two would be playing the major role. So as far as the advantage is considered, which one do you prefer? Which one is more advantageous to manufacture? Is it alkali activated concrete or geopolymer concrete?
Yeah, that depends on the application. And I know that the Davidovich, you know, Davidovich is like a, let's say, father of geopolymers. I would recommend you, if you don't have, but probably you have the book from Davidovich. And he has a very strong definition of the geopolymers. And on the other side, you have John Provis, who is more, you know, alkali activated materials. Actually, probably, you know, there is, you know, they don't, the Davidovich doesn't actually agree with the alkali activated materials term. He doesn't like it, but, and he has actually some arguments, chemical, why is that you cannot call it alkali activated materials, which I understand. He's actually right also. But on the other side, he also has calcium in geopolymers, so that makes it more difficult. He also puts the Davidovich, he also has, and he also says that's actually the best mixture is the geopolymer mixture with some calcium inside. And I think it's around 5%. I'm not sure how much actually this is. It's, but yeah, it depends on the application. But I think it's good to add some calcium inside, some slag, and then you actually have less porosity, more disconnected pores. The problem of geopolymer is that the pores are very small, which is good, but they are connected, and the drying, shrinkage, cracking is problematic. But if you add calcium, you are basically lowering this very small porosity, gel pores, and then you have less porosity, so it's good to add some calcium. But then you have maybe, yeah, setting problems. Yeah, it's, I don't know, we work mostly with pure geopolymers, but I think it's better to add some calcium also inside. This is what we are doing now. It will improve the properties for sure. But to go all the way to the other alkali activated system with a lot of calcium, yeah, then you have less activators. You are correct. And this is, but then you are more in cementitious systems because you have basically calcium, alkali, silicate hydrates, SNASH. And in the geopolymer, you have more of this, you know, 3D connected, the full polymerized network. Then Davidovich says that in alkali activated materials, although he doesn't like the term even alkali activated materials, you are basically, it's just cementitious material with more alkalis in it. It's, yes. Yeah, I don't know what is, it depends on which applications you want. I think the real geopolymer, let's say less calcium, this is really, it's more expensive. It's more, you need more alkali activator. It makes it more expensive. But if you have a high-end application like durability, high-tech material, then it's justified. And then you should have, like acid resistant. There should be a reason why you go for pure geopolymer. But otherwise, it's much cheaper to just do normal alkali activation with less alkalines. And that means more calcium, which is basically just a little bit modified cementitious system, alkali activated system. Yeah, there is a big discussion between geopolymers and alkali activated materials. But I was on this day with I actually understand both sides. I don't take any side. I was also with in this. You have geopolymer camp every year, organized in France by Davidovits. Now also his son Ralph Davidovits, he is taking over. You can see it also in LinkedIn. He is now leading this research in geopolymers, and they really do great stuff. Of course, they are the founders, and now son is taking over. And I was in this geopolymer camp 2 years ago, I think, or 3 years ago. And it's really nice. You really understand. It's very nice. I would recommend you, if you can have a chance, go there. Go to the geopolymer camp. It's also a very nice company, very nice environment. It's really like a camp, but you learn a lot.